Okay, so we're going to, in this podcast, learn how to write addresses for electrons, their configurations, orbital notations, all of which are the same thing, talking about where electrons are located. And in order to do that, I like to teach it using the periodic table, where you can actually just look at it and know that there are different blocks, and those blocks dictate where those electrons go. So the first two groups of the periodic table, the alkali metals and the alkaline earth metal, are considered the S block. They are always the first two electrons in any shell. So the first shell actually corresponds with the first period, the second shell, the second period, third shell, fourth shell, fifth shell, sixth shell, and seventh shell accordingly. Okay? So this is the shell. First two electrons in a shell are always S electrons. Okay? The last six in the shell are always P electrons. 1, 2, 3, 4, 5, 6. So this is known as the P block, the last six columns. Now helium's kind of an oddball. We'll talk about him separately. So S and P are the main group elements, or electrons, but there are also other electrons known as the Ds, which is where transition metals are being filled, in the F blocks, where the inner transition metals are being filled. And we'll talk more about those in a little bit. They'll become a little bit clearer. And basically what we do when we add electrons is we simply go across the periodic table, across and then down. Across, hydrogen to helium. We go into another shell. We add S electrons, we add P electrons, we add another shell, we add S electrons, we add P electrons. So let's take it through the first few rows. Okay. Before we do that, though, there are three principles that guide us in writing electron configurations. The first is known as Aufbau, the second is Pauli's exclusion principle, and the third is Hund's rule. So the Aufbau principle says electrons will occupy orbitals of lowest energy levels first. Okay? And so here's a picture of the potential energy of electron orbitals. So the lowest energy orbital is a 1s. First shell, S electrons. Okay. The second is the second shell with 2s electrons and 2p electrons. Okay. The third, and I'm calling these shells, are also called energy levels. These are like the layers of the onion. Okay. The next energy level is 3s, and there's 3 S's, P's, and D's are here. 4s are here. And one of the things you'll start to see as we do this is that the 4s and the 3d are very close in energy level, and the 3d is actually lower than the 4p. Alright, so we'll talk about what that means as we get there. Okay. Then there's the Pauli exclusion principle, and the Pauli exclusion principle says no two electrons can have the same address. So if I were to I use an analogy, I say I'm inviting you to a party, and if I just tell you that I live in Pennsylvania, do you have enough information to locate me? And the answer is obviously no. So if I tell you I live in Glen Mills, Pennsylvania, do you know could you find my house? The answer is probably no. You're a little bit closer, but you still can't find my house. So I need to tell you that I live at 46 Mendenhall Drive. Well, if I told you Mendenhall Drive, that's still not enough. I need to tell you 46 Mendenhall Drive, Glen Mills, Pennsylvania. You need 4 pieces of information to find my house. Well, electrons exactly the same way. You need 4 what's called quantum numbers to identify the location of the electron. The first is the shell or energy level. We call this N. So the first shell is called energy level 1. Second is energy level 2. The second is the angular quantum number. Now that's just a fancy word for the shape. We talked about those S, P, D's, and F. You need to know S is spherical, P is those figure eights, and people call them dumbbells. Okay. The third is the magnetic quantum number. So for instance, if I have a P orbital within a shell or an energy level, there's 3 P orbitals. There's one here, which might be the x-axis, one here, which is the y-axis, and another coming. This is 3 dimensions, so there's a third dimension, which is the, okay, so this is the orientation, and the fourth would be the spin. And what it says is each orbital can have up to 2 electrons, so it's either got 1 or it's got 2, and if it's got 2, they have to be opposite spins. Okay, So we use plus a half or minus a half to discuss spin. So the important thing is to know that in order to identify the location of it or the address of an electron, I need to use 4 quantum numbers. Okay. The last rule is Hund's rule, and it's often called the school bus rule. So again, I'm going to use an analogy. If you were to get on the school bus in the morning and you're just on bed, you're at the bus stop, you run to the bus stop, you get on the bus, it's half empty. What are you most likely to do? Are you most likely to sit on the seat by yourself, or are you most likely to sit on the seat beside someone that's already there? And most people would say they're going to sit in a seat by themselves. Well, electrons are the same way. They occupy their orbitals singly before doubling them up. So what you find is every seat has a person in it before you start to find 2. Okay, so within an orbital, electrons are going to go singly before doubling. Alright, so let's actually go through some. So here's hydrogen. It's the first element. It says right here it's a 1s electron. So that means here's the nucleus. It's got 1 shell, and it's an s orbital, and I have 1 electron. So I'm going to put the electron there. So I can draw what's called an orbital notation. So I put this little box, I have a 1s orbital, and I've got 1 electron with a spin, let's say an up spin. I can also write that as an electron configuration, and I just say I have 1s electron with 1 electron in it. Okay? So the next element is helium, and helium has 2 electrons. Now, some people think this helium should be over here, because it's also an s electron, which is why it's blue. Okay, so I have 2 electrons in my 1s orbital. They have opposite spins. That would be my orbital notation. Or I could write it like this, electron configuration, which doesn't show the spins, just says I have 2 electrons in the 1s orbital. Okay, so I am here now, and I have a full valence shell. So the next element is lithium. Now lithium, is right here. Let me go back to lithium. Is right here. So I need another shell, because this is the second shell. So I add a shell, and I need to add, this is a second shell, starts with a 2s, just like, sorry about that. So I've got 1 electron in my 2s, so I have a 1s2, this is filled, and I have a 2s that has 1 electron as my electron configuration. Okay. Next element is beryllium, which is 4 electrons, it's atomic number of 4. So I've got 4 electrons, so I have a 1s2 right here, I have a 2s2. They're both full, they have opposite spins. I can write it as an orbital notation indicating the spins, or show it as electron configuration. Then I have boron. Boron is here, so this is the p block, right? So my s is filled, so now I need a p block. And when I get into the p's, there are 3 p orbitals on the x, y, and z axis. So I have 1 electron in the p orbitals, and it's in the 2px block. Okay. I get to carbon, and now I have 6 electrons. So I have, this is where Hund's rule comes in, right? I put 1 electron in each of these orbitals before I double them up. Okay? Now as I go to oxygen, I have a total of 8 electrons. I've added another electron, and again, I've singled them up, now I start to double them up. Okay? This is fluorine and neon. Okay. So here I have sodium. I need another shell. I've added another shell, another electron. This is my 3s. Okay, so I'm just going across 1s2, 2s2, 2p6, 3s2. So I've got 3s. I've only got 1 in here so far, right? Magnesium, I've got 2 electrons. Now let's say chlorine. Alright, so I can look at the periodic table and say chlorine is in the p block. It's in the 3p, and it's right here. So I've got 3p, 1, 2, 3, 4, 5, 3p, 5, and here they are, p, 1, 2, 3, 4, 5. Argon has a full 3p full. Okay, I've got 8 electrons in the valence shell, noble gas. I'm going to drop the orbital notations now because they just get too complicated. Alright, so now I'm on potassium. So I'm on the fourth shell, and it's important to do the fourth shell because something strange starts to happen. So I have the fourth shell, I have one electron there for potassium, so I'm just adding to what I had for argon. Calcium, I have my 4s is now full with 2 electrons. But what happens next is I have scandium, which is 21. And what you'll see here is that the next electron does not go in the valence shell. The only electrons that go in the valence shell are s electrons and p electrons. I'm in the d block now, and d electrons go inside one shell. Alright, so this is the 3d1. It goes inside. I put it right here. Okay, so I still only have 2 valence electrons. If I go all the way across to zinc here, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 d electrons. So I've added them all inside the valence shell in the third shell. So I have a 3d10. Okay, and if I add all these numbers up, they should add up to the 30. So let's see what happens next. So I'm right here. I should be going into my p block, but it's the 4p. Okay. Okay. So gallium 31. I add another electron. This is the p electron, so it's a valence electron, comes out here, and now I have a 4p1. So I went from a 3d 4s to a 3d back to a 4p. I'm back on the valence shell. Okay. So let's just take a look at the blocks here. So we have the s block. There's one orbital. It's a spherical orbital, and it holds 2 electrons. When I get to the p's, within a shell or an energy level, I have 3 orbitals. Each can hold 2 electrons for a total of 6. Remember, the p's are shaped like a figure 8, and there's 3 on each of the 3 axes. So there are 3 p orbitals. Each can hold 2 for a total of 6 electrons. For the d's, if I count across, I've got 10. And what I know is each orbital can hold up to 2. So I must have 5 orbitals here. Each can hold 2 for a total of 10. When I get down here on the F's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 across, 14 electrons must mean I have 7 orbitals. Okay. Alright, so let's take a look at radon here. Now, when I get down to radon, we need a shortcut, right? It's going to take forever to write this. So what I can say is radon, hold on a sec. Alright, so I want an electron configuration for radium, and what I can say is radium is just like the noble gas radon. We call these the noble gas shortcuts because we use the noble gases. It is just like radon, that has an atomic number of 86, plus it's got 2 more electrons. It's got 2 7s electrons. Okay, and this should add up. 86 and 2 gives me 88, which is what radium is. Okay. So to make a noble gas shortcut, what I do is I find my electron, my element, I go up a row all the way over to the noble gas. In this case, it was radon, and I put that noble gas in brackets, and then I add whatever electrons I need on the row that the element is in to get me the full complement of elements that are, or electrons that are there. Okay, so let's take a look at another one. Alright, so let's take a look at arsenic. So arsenic is here. It's number 33. So what I do is I go up a row to argon, which is the noble gas. So it's the same as argon, which is number 18, plus I've got to do whatever I need in this 4th row. So it's 4s2, 3d10, and then 4p, 1, 2, 3. Okay? How about let me see, rubidium. NB is right here, it's going to be the same as the noble gas above it, which is krypton, number 36, plus 5s2, and then 1, 2, 3, 3d3. Okay. Alright, let's look at PA. PA is down here at 91. So the F electrons, it's important that you know F electrons go 2 levels inside the valence shell. D's go 1 level inside. F's go 2 inside. So we want to take a look first at, oops, here's the F block. We put it down here, and the only reason it goes down here is because if we placed it where it belongs and printed the periodic table this way, it's just too long. It's too hard to, it's impractical to print and hang. So what someone decided to do was take out these elements, the F elements, and pull them down. Okay. Now you see some different conventions. Some cases they start with CE and TH down here. In some cases they start with LA and AC down here. Okay. So always be aware of which table you have. So if the F block really belongs here. So this is row or energy level 1, 2, 3, 4, 5, 6. So I'm in the 6th energy level, and I got 6s. Once I do 6s, I'm going to do 4f because I go inside 2, right? Followed by 5d, followed by 6p. If I have 7s, it's going to be 7s followed by 5f, followed by 6d, followed by 7p. A little bit confusing until we've done it a few times. So let's say we have PA, which is down here. Okay, so that is going to be the same as, so PA belongs up here, right? This whole block belongs up here, so it's in the 7th row. So it's going to be the same as radon, 86, plus 7s2, plus 5f3. 1, 2, 3. Okay. If I look at iridium here, okay, it's in the 6th row, so I go up 1 energy level. Xenon is the noble gas. Put that here. Go down to the row it's in, which is 6, so it's 6s2. All of these F's are here, so 6s2, 4f14, there's 14 across, and then 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7 across, 5d7. Alright, so let's talk about electron configurations of ions. Alright, so let's say I have sodium. Sodium is going to form a +1 ion, and when it does that, it loses this electron and it loses its shell. Right? It loses that whole 3rd shell. So this electron comes off, and I am simply left with 1 less electron. So I have all of these, and I've lost this one. So doing ions, electron configuration is pretty easy. Figure out whether it's gained or it's lost. Take what it started as, add it or subtract it from what you have. Electron dot notations are pretty simple too. All you are doing is showing valence electrons around an element. So they also follow the Hund's rule. So for instance, if I have carbon, I do 1, 2, 3, 4. The most I can have is 8, right? Because it's just S and P electrons. The most I can have is an octet. So we put them on different sides, and we don't start doubling up until I have 1 in each seat. Okay, that's going to do it.